Okay, for this video we're doing more examples of L'Hopital's in action. So I'm going to take this limit and I have e to the infinity over the square root of, e to the negative infinity over the square root of infinity. Well, e to the negative infinity is the same thing as a 1 over e to the infinity. So basically I'm saying that this is 0, this goes to 0, it's 1 over e to infinity, times infinity. So I have 0 times infinity, which is indeterminate. We don't know what this is equal to, but it's also not set up for L'Hopital's. L'Hopital's is 0 over 0 or infinity over infinity. So what you want to do is go back to the problem and see if there's an easy way to change it into something that L'Hopital's works for. And there is. This e to the negative x can be written in the denominator. So I have the square root of x over e to the x. And this is now the limit as x approaches infinity of that. And this is not an application of L'Hopital's. This is just algebraically changing the way it looks. So if I plug in infinity right now, then I get the square root of infinity is infinity, e to the infinity is infinity, and since I have infinity over infinity written in this way, I can apply L'Hopital's rule. So I'm going to say that this is the limit as x approaches infinity, and I'm going to take the derivative over the derivative. The derivative of the square root of x, I can rewrite that as x to the 1/2. So it'll be 1/2 x to the negative 1/2. And then the derivative of e to the x is e to the x. Well, if I rewrite this, this is the limit as x approaches infinity, the 1/2, I've got a 1 in the numerator, a 2 in the denominator. This x will actually be in the denominator because of the negative exponent, and it has a square root. The e to the x stays in the denominator. So now when I actually evaluate my limit, I take my infinity, I plug it in, and I have 2 times the square root of infinity, which is infinity, and e to the infinity, which is infinity. So this is 1 over infinity. 1 divided by something really, really large is really, really small. So the answer to my original limit is 0. Another example, we're going to do the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. Now, it's really helpful to know the graph of the natural log of x when you're evaluating limits. I do it all thinking about the graph. So I know that this is 1, and I'm actually approaching 1 from the right-hand side. So the natural log of 1 is 0. I'm approaching from the right, so this is actually 0 when I evaluate it, but on the positive side of 0. Minus, and then this will be a 1 over, I take my 1, I plug it in, 1 minus 1 is 0. Okay, but I need to check the sign of this 0, so I could do it graphically or I can just evaluate. I'm going to pick a number close to 0 but to the right of it, so like 2. 2 minus 1 is a positive, so I have a positive there. So both of these will be the same thing. So this is 1 over something really, really, really small, so it's huge, it's infinity, and a positive divided by a positive is positive. So this is positive infinity minus a positive infinity. Well, this is one of our indeterminate forms, but it is not something that's ready for L'Hopital's. That has to be infinity over infinity or 0 over 0. So I need to turn this algebraically into a fraction. So the key there is just, actually subtract the 2 fractions and change this. So this will equal the limit as x approaches 1 from the right. I'm going to get a common denominator. So I'll multiply my 2 denominators together, and I have the natural log of x times x minus 1. So since I multiplied the denominator by x minus 1, I'll multiply the numerator by x minus 1, and I'm subtracting, and then on this fraction I have to multiply by the natural log of x. So if I plug in now, I have 1 minus 1, which is 0, minus 1, which is 0. Then the natural log of 1 is 0 times 1 minus 1, 0. So I have 0 over 0, and this problem is ready for L'Hopital's. So I'm going to take the derivative over the derivative, The derivative of x is 1. The derivative of negative 1 is 0. The derivative of the natural log of x is 1 over x. Then in the denominator, I have the product rule. So it's the first function times the derivative of the second, which is 1, plus the second function times the derivative of the first, a 1 over x. So if I plugged in right now, I have 1 over 1, which is 1. 1 minus 1 is 0, so I have a 0. The natural log of 1 is 0. Then 1 minus 1 is 0 times 1, so I still have 0 over 0. So I'm going to apply L'Hopital's again, but I have some choices to make, and what I can actually do right now is clean this up a little bit. So I'm going to multiply by a very clever of 1 here, and so I'm going to multiply by x over x. And what that'll do is get these x's out of the denominators. So this is still equal, it's the same limit, and I'm not taking the derivative, I'm just simplifying it algebraically. So I distribute this x, and this is now x minus 1, and you can see that that's a nicer derivative to take, over x ln x plus x minus 1. And if I plug in, I should get the same exact thing. I haven't changed the value here. So 1 minus 1 is 0. 1 times 0 is 0, plus 1 minus 1 is 0. So now I'm ready for L'Hopital's. So this is the limit as x approaches 1 from the right. The derivative of x is 1 minus 0 over, and then I have to do the product rule again. So it's the first function times the derivative of the second, plus the second function times the derivative of the first, which is 1, plus the derivative of my x is a 1, and then the derivative of negative 1 is 0. So what I have here, you can tell, is that I have an x over x, so that's just 1. I plug in the natural log of 1, that's 0, but I have a 1 here and a 1 here, so in the denominator I have 2, and in my numerator I have a 1. So the answer to my limit is 1/2.